All right, we can begin here. Now, going forward, basically, what did we first learn in our first session? So, what we had started basically, we started with what did we start with? We started basically with the first thing that we started. We actually tried to predict. We tried to predict linear data. Linear data. We were working with linear data. Okay. Now, then there was we just predicted that linear data with simply no sequential, I mean, with a very plain model. And what model was that? Simple sequential model we had. And in that sequential model we had input layer, right? We had no ReLU and we had an output layer. Simple. In fact, first we started with a simple linear layer only. The first example was a one neuron only. Then we actually made the problem a bit more complex. Then we wanted to learn over non-linear data. We wanted to learn over non-linear data. Okay. So in non-linear data, basically what we did was we introduced the activation functions like ReLU and Tanh, right? So basically this is for linear data, this is for non-linear data, anything like this, right? So it will be able to predict that non-linear data. It's quite simple. And then after that, uh, still we have to take it forward. We understood what is ReLU, what is Tanh, how does ReLU differs from Tanh, right? What are the differences between ReLU and Tanh? And these are internal functions, that is, we will be using them inside the model only. And we'll continue to use them inside the model. I mean, all of our examples are not now going to use all of these things. Not just that, we actually also discovered our very small training example wherein we first define a model. First, we define a model. After defining the model, we define a loss, and then we loop over our loss. That is how many rounds of training, number of rounds of training, right? And after rounds of training, basically calculation of loss, then back propagation, right? Back propagation, and then resetting the gradients, no grad, right? Resetting the gradients. So this was basically what we were doing earlier, and we will continue to do this. I mean, in just some amount of time, you will understand that okay, this is the basic structure. Except for in future with sequential, we will just learn to create some more complex models, right? So yeah, after today's session, maybe today we will also continue to use sequential, but then we will have one session to understand how to create more complex models. But for today's session, I guess sequential is just fine, right? Now, as we go forward, uh, all of this data, if you see here, all of this data is continuous data. Now, what is this continuous data? And a new term that I introduced, nothing. I mean, if you just see a continuous data, you have always been seeing continuous. And so what is continuous data? Continuous data is this kind of data, anything that can be plotted into a graph, and this is continuous data. Non-continuous data is, let's say, there are some, there are some dots of red color present here, and there are some other dots of, let's say, green color that are present here, right? And there are some other dots of, let's say, black color that are present here. This is not continuous data, right? uh, do we encounter these kind of non-continuous data? Yes, a lot. Do we encounter these kind of continuous data? Yes, a lot. Let me first try to give you a few examples, right? First and foremost thing, let's say anything regarding, these kind of data, these kind of graphs are very common. The first example is basically any stock data. So basically, when I say stock data, it can be anything, your company data, finances, financial data, right? Then even used in inventory data, inventory data, sales data, sales data, right? And the list fraud detection. That is, fraud detection comes from some kind of, we will have some kind of, that okay, this is the transaction, these are the list of transactions. So in fraud, usually how it happens, we have a new concept called as, we call it as anomaly, but this is nothing new. Let's say the transactions are happening like this, and there is suddenly a spike here in the some kind of volume or something. Now this is an anomaly. Anomaly means this is something unusual, right? Unusual, right? So even this is a different thing. I will cover one lecture on it, because uh, I mean, just anomaly, there are companies that are just doing one thing, that is unusual data detection, fraud detection, all of your credit cards fraud detection, any of your security compliances breach, all of that is happening through unusual or anomaly detection, right? Unusual pattern detection, you call it. So all of this is continuous data, right? This is continuous data. Now, slowly you have to understand the data, because as you start understanding the data, 60% of the problem gets solved there itself. And then slowly we will cover how to handle all of these different kinds of data. Two major things that we have covered, right? Any, if you are dealing with any kind of financial thing, this is the thing you are going to get with. Obviously there are more advanced method apart from these two things that we have studied, but do not underestimate logistic regression, that is, the regression that we studied was a non-linear regression, right? Do not underestimate it. This is very much in, like I told even in the previous session, it is very much in use, right? It gets used at lot of places. Now in logistic regression, the advanced parts are basically we keep on adding more and more inputs. We try to find relationship between more and more inputs, right? The number of input parameter increases, and thus basically your section of logistic regression also starts getting more complex, right? And now we talk of non-continuous data. Non-continuous data, a lot of data is present in non-continuous format. Basically all of the classification problems are non-continuous data. Now what are classification problems? Classification problem, let's say first is a very simple or non-practical example, like dog versus cat classifier, or we can call it anything. Basically it can be classifying your image basically into category 1 or category 2. It can be anything, right? Anything you can call it, mountain versus sea, or whatever you wish to call it. Then actually the real time thing, what comes into picture is basically sentiment analysis, right? Or sentiment analysis is basically like, if in your this is very much used in the marketing. Let's say anyone has left any comment, so what is the overall sentiment for this post, or overall sentiment of your reviews, overall sentiment of your products, right? These kind of things. Then even fraud detection also comes in this part also. So fraud detection here is basically automatically classifying the data, that if it is normal or if it is abnormal, right? Then very common that you find always in your Gmail, spam versus ham. Now, these are all text. We are going towards text, although spam versus ham, right? Anyways, this is all data. The whole point being, it may be image data or whatever data it may be, it is data. So basically, my model now needs to learn over non-continuous data. We have learned over continuous data, but now we need to learn over non-continuous data, right? So this is what today's session will be. We will take a leap from continuous data and we'll walk towards non-continuous data. But we will actually revisit this continuous data, because text uh, have to be handled using both of these approaches. I mean, we'll have to mix these approaches. So we'll cover one more advanced technique in continuous data, that is LSTMs and RNNs, and then we'll go towards basically transformers or the generation models, right? So yeah, I mean, we'll revisit this topic maybe tomorrow or next to that class, right? Now we will be talking about this section here. Okay, now going forward, that what are we going to, how are we going to start with this? Obviously we are going to start with practicals, right? First we will have to visualize that what does my non-continuous data actually looks like. I mean, what is my non-continuous data? So first we will take some sample data, that is some synthetic data that is not real world data. Right? We'll start with, let's say, some synthetic data that is not the real world data, and then gradually we'll move on to the real world data. Right? Some so okay, we'll try to visualize some data that is synthetic in nature, and then we will see that what how does my existing model treats that? How does my existing model treats the new data, and then what are the changes that I need to make in this new data, right? So this kind of data will have something like this. Okay, so let's get started basically. So I'll just go ahead and I'll create a new collab basically. This will also become your exercise, right? I'll go with a new collab, a notebook. Okay, so here we have, and basically let's say exercise number, I guess 6 is something that we'll be going towards, and we talk about non-continuous data. Non-continuous data or classification problem, or the classification problem. Okay, so first and foremost thing, I will again go back to my sklearn in order to make the things easy, and the data set name is basically moons data set. It is, and this time in order to expedite the process, I'll just say here that use sklearn and create moons dataset and visualize it. Okay, so here we have simple dataset, that is make moons is the dataset. How many number of samples do we need? What is the noise that we need? Now, if you remember, this is something we had been doing manually till date. We have been generating the noise in the previous section. Noise is basically how much of, not smoothness of the data you do you want. So I'll just take more data so that we have enough data to train. So I'll just take this and I'll just try to first visualize this data. Let it connect, and okay, so here is my output, and you see this time it is continuous. These are non-continuous points basically. Now each and every data represents some point, right? And this is again very simple example. Basically we are just taking two data points here, right? A very simple example that we have. Now, what I would like to do is I would either ideally like to simply, run my previous program here. That first I want to run my previous program, and I would like to see that what happens when I'm trying to run my previous program here. So in my previous program, I was simply using mean squared error loss. So now even in this case, 90% of my code is going to remain same. Like I said, you just need to understand that basic code, and most of the times it is going to remain same. It is just the models and the model architectures that will keep on changing. And we'll see why it changes, why it doesn't changes. Right. Anyways, this is the data set, and now I want something that I should be able to differentiate between this data and this data. Although this is a visual data, but next we'll move to some complex data. But first we'll have to understand the technique basically. So going forward, the next function I can start with is basically I will need to convert this data into tensors, right? And then after converting them into tensors, I will, okay, right. Let's first start converting them into tensors. Just wait a minute. We need to visualize this. Right. Anyways, let's start with, you know, generating. So here, the next problem after we have visualized is we will convert our data into tensors. Uh, we need to find out that what is the type of my data, so that I can use that respective functions, you know. So let's try to first know the type of my data. So I'll just get the type of my data. The type of X, it is numpy array. So I'll use from numpy torch again. Torch to tensor was the function, right? So X underscore tensor, I'll use X underscore tensor is equal to torch dot from underscore numpy. Import torch is not done, I guess. Go with import torch, right, from numpy. And what is my data here? So basically I'll just take the X data. Let me take the X data. Okay, done. But I guess there is one more thing we'll have to take care. Like I told you earlier also, X of 0 to 10. First, just try to find out your data should not be in proper integers. I guess the numbers are in float. Okay, that is fine for us for now. Right. Okay. X is done. The same we'll go for Y underscore tensor. So Y underscore tensor is equal to torch dot from underscore numpy. Right. And Y, the variable name is simply the Y. Right. Okay. Y underscore tensor and X underscore tensor is done. Next is my model building. For now, I'm going to take the same model, right? So I'm going to take the same model. The same one model is equal to Nn dot sequential, right? And in sequential, this time my input layer, I need to define that what is the input that I need to take, right? So I'll simply go for nn dot linear, two input layers, and let's say the hidden layer I'm going with 20 hidden layers. And next is nn dot ReLU. I will have to import this nn, import torch dot nn. That's right. Nn dot ReLU, and simply nn dot, right, linear of. Now basically here is exactly the difference in the model that I'm trying to bring. Now in my earlier model, basically what I wanted, what I want with this data here, basically in this data, I want to differentiate between these two data. So how can I do that? Basically, till now, I wanted only one output because I was basically trying to predict a continuous data. Right? Now, this time I want more than one output. If let's say this is my data, earlier what this is my single line, right? And I, let's say I want to predict that what is going to be the future next. So I want a single output, right? There is one output that I want. But this time what I want is that, you know, I have this and I will input that this is my point. Let's say I will give it a input of, let's say, point X. These are the actual points. These are so, and what I want is I want my model to tell me to which category does this belongs to. So hypothetically we can say that this is category A, this is category B. So I want my model to tell me that to which of these categories does my model belong to. So ideally, the ideal or the most uh, best way to do is, now I am not saying this is the only way, because I'm not saying this so that you can go ahead and experiment. I'm not limiting your uh, like the appetite of experimenting, but yeah, most of the times we use that, we give that either A is 90% and B is, let's say, 10%. So eventually it will tell me that, okay, I need two outputs. What is the percentage for A and what is the percentage for B? So this is what I want, and this is how I'm going to train my. So how do I do that? Basically, my, again, input and output, the same rule of input and output, right? My input and output. So let's try to find out that what is my input and output. How does my input and output looks like? So I'll just go for, although we just converted it, but we can just go ahead and see that what does my x looks like, x of 0. So it has two inputs here, right? That is, it is basically having two inputs, and then I go for x of 0 and x of 10. Okay, it is having two inputs. Now I need to consume this two input data, and then I'll be splitting out basically again y of, let's say, y of 0. If I go for, now it is actually giving me one label only, right? But how do I decide that it is going to be one label? What I'm trying to do is basically, I will try to take these two variables and I'll try to map it with my output. My output is going to say that, okay, this is category A or this is category B. So what it has given me, if you see, these are categories it has given, y of 0 to 10. It has given me simple labels. It is giving me simple labels. So what I want is that, okay, I'll take this input, and now I want that I'll take this input and I will tell my model that, okay, this is my input. I'll tell my model here that, okay, you want to predict A is this many percent, B is this many percent, and then finally I will make a guess that, okay, since A is greater than 90%, so it should be A ideally. So basically I want two output neurons here, because this time I'm going to guess for non-continuous data. So, and I have two categories. What if I had three categories? We'll look at that example also. If I had three categories, I would have taken three output neurons here. In that case, I would be going on with three output neurons, right? Instead of this. So here I'll just go for two for now. Okay, I guess. Okay, my model is there, right? And I can even just for, I can go ahead and print my model. Okay, this is what my model, this is what I prepared also, right? And then basically next is something very important. What I was doing is, right, okay, I used to prepare basically an optimizer, right, that will help me in updating my weights. So this is the same optimizer, right, SGD, right? This was the optimizer that I was using, and then I also need one loss. Okay, now it is automatically detecting, my model is automatically detecting, saying that nn dot cross entropy loss, right? But I have to demonstrate you that why I should be using this. But so first we'll go for nn dot mean squared error, MSE loss. I'll go for this, right? This is same, I guess, what we were using. So okay, this is done. And next is very simple, that we will have to use the same loop, that how many times we were iterating over the same loop. So I'll go with epoch. I'll go with 10 epochs, and for epoch in epochs, for epoch in epochs, I'll model dot set the model in the training mode, model dot train, and then output model dot x underscore, right? X underscore tensor, the same thing that we have been doing. And I'll go with output. Output is equal to this model dot x underscore tensor. And next is we'll go with the loss. We might face some error for basically arrays, I guess, the dimension of the array, size of the arrays, but we'll see that. No worries. Right. So I need to calculate my loss with respect to output underscore output comma y underscore tensor. Right. This is how it is going to calculate the loss. And then I can go ahead basically just with optimizer dot. I'll add this loss so that I can loss underscore history. So this is basically just to add up so that I can track it once I am done with my training. I can track it that what my loss has been for plotting it to the graph. Okay, loss dot history and optimizer. Okay, it is automatically telling me that optimizer dot zero grad loss dot backward and optimizer dot step. Let me print this loss at least. Print loss, the same loop that we have been using till now, and we will use it regularly the same until unless there is very much complex. Even for very much complex, there will be some small operations here that we'll have to just print it here, right? And that's it, I guess. Now let me try to run it. Okay, int is not iterable. Epoch is okay. Sorry for that. Yeah, got it. So basically, the problem lies here. Yeah. So when we are converting to tensor, so I need to make sure that I'll have to make sure that it should be in float 32. So I'll just give it as from numpy x comma as to as time, I guess, right? Float np dot float 32 import numpy as np. And then okay, let me try again. Same thing again. Non-singleton dimension 1 y dot tensor. Why is it criterion? I guess it has to be. I'll try with nn dot, because my model, I've already taken the model, I've changed the dimensions of the model. Yes. So basically what was happening, I mean, since I have already taken it as 2, so mean squared error usually works in 1 dimension. I mean, since I have already taken it as 2 dimensions, so this might be causing an issue. So if I use it 1, then obviously I can use criterion like this. Don't get confused with so many options that it is giving, right? These are just the same things. It is again the same problem, I guess. Output is same. Okay, output we have already. Okay, all right. Now it is giving error at this point because this one. Okay, fine. So ideally, what we want is this time we want to give 2 dimensions here, and after giving 2 dimensions, I want just the only change that will happen is instead of mean squared error, I will get cross entropy loss. And once I get cross entropy loss, let me see that again. Oh, this time I'll have to reinitialize the model. Hold on. Okay. And my loss is actually not getting very much down, but if I just try to visualize what my loss has gone down very partially. I mean, from 0.67. The reason is that I guess it has very easily learned, to predict this model. I mean, since the data was very simple, so it learned at a very initial stage. Or I'll try to go with epoch 100. So yes, now the loss is even subsiding further. Okay. Now, basically, what I want is, let's say what we have done here, we just tried to print this data, the loss function. However, the complexity has now increased. In what sense? That is, since now my data is not this way, that I can simply depict it that this is how my model is learning. But can it not be done? No, that is not at all the case. We can actually cover the area. We can cover the area, that this is the area in which category A is being highlighted. Till the time our data is 2D, even for 3D, we will be able to do that. And I want to display that, okay, this is the area in which the 3D, in which the category B is present. So as of now, I'll just go ahead. First, I'll try to simply print this data. Right. Let me just try to model dot eval. I'll set to evaluation mode. And then now I need is output. Again, output is equal to model extensor and predict, right? Predicted functions. So if I see dimension is equal to 1 torch dot max. Now this is my prediction on the data that has happened. Now all of the prediction has happened. If I go ahead and let's say I'll have to plot this data properly. Now it has to be a scatter plot, basically scattered. Why it has to be a scatter? I'll take the help of, can you plot the predicted on scatter plot? Now this is actually the predicted data. The predicted data, so we have been able to, this is the error point, this is the error, because if you see the original data, this is my original data. So my original data, what it is doing, that my original data, this is my category A, but here what it has done, it did not learn it properly, so basically it automatically included this into category A only. So what can I do? I mean, there are many things I can do. I can first go ahead and increase my layers. I can go ahead and increase my layer. Let's say I'll go for 100 layers, and I can go ahead and increase my, I need to be sure that, okay, this is 100 and this both should be matching, 100 and 100, and then it can go back to some 100, and I'll have to include one more ReLU here, one more ReLU, and then again from 100 to 2, right? We'll just try to modify this and epoch 100. Okay, it has, the error has gone down, but not to that extent. I mean, not to very huge extent. Again, this problem is still here. I'll try to increase my epochs this time. This time, if you also see some of the things that have completely gone out, is basically I'm not as of now directly configuring my what is the training rate. Now, is it the case that we are not at all using the train? No, that is not the case. But yes, training rate is automatically being considered here. So it is automatically taking the training rate, and we'll come into that point later on. Let me go for 500 epochs. This time it has gone even down. It did improve up to a certain extent, but not to a great extent. And then the error has further gone down. Okay, if you see it is improving now, I'll go more. I'll go 2000. Although you should be very careful with increasing this. The reason being, if you increase it too much, it will not work on unseen data. I mean, for demonstration purpose, obviously I'm trying to show, but it will not work on unseen data. That is new data. Now it has already, this time it has actually, you see, it has been able to learn this data. It was able to learn that whatever category is present in category A, whatever is present in category B, it was able to do that, right? How do I actually predict my data? So basically, this is my predicted data. Now, in my predicted data, if I go and predicted of, let's say, 0th, which is giving me, because I have done is torch.max from the output. If I try to print what is output of, let's say, 0th point, what did my model gave me 2 points, right? Model gave me, this is the probability of two categories that it is giving me. Now what torch.max has given, it has automatically, because this is what we want to do, it has automatically selected the maximum one. Now, you might also say that this is not probability. That is very much true. Your model is not supposed to actually return, your model does not guarantees you to return probability. Later on, we will have to convert this into a probability, right? There's a simple function, right? What is a probability? A probability is that both of these numbers should add up to 1. One is 60%, other is 40%. One is 70%, other is 30%. These both are not probabilities. As of now, we are just selecting that what is the maximum of them, and if someone is actually the maximum, then we are actually selecting it, right? And it is able to tell me that, okay, this is what your probability is, this is what your predicted number is, you know. But in real life, ideally, when we go forward actually with the more complex examples, there are few more complex examples that we have to study. But before that, we also have to understand why did we choose cross entropy, because this becomes very important for you to understand in the future models. How do you select your loss function, right? So here ideally there would be one more function, convert these model output to probability. By default, model is not going to return. Model is simply a number engine, right? So all it returns you is plain numbers. Even if you go for one, we go for something like this, so it is simply returning me number engines. Yeah, Keyur, please go ahead.
Yeah, Anand, as you said, right, in the previously the conversations that learning rate we are not defining here.
Correct, correct,
So,
correct, correct.
because in the previous assignment, I have seen that you have passed the learning rate as well as the epoch.
Right.
So why, how it can be difference? Like in previous one, we required to pass, and that's so one of the torch method where we optimize the our model right through those parameters. So, but here, how it will consider that?
Yeah, ideally, so learning rate is present. It's not the case that learning rate will not be present here, but we are already considering a default learning rate as of now. I did not mention it here, right?
Okay.
Now, yeah, when we go further with some more complex example, their learning rate will be present. I just mentioned that, okay, learning rate is not present here, right? So initially it is not present, but yes, learning rate will be there. I mean, there is no learning without learning rate ideally.
Okay. So how defaults there should be taken as a default, is it? Then
Yes,
if
ideally, in these cases, it will take as default.
okay. Okay.
right? But yeah, I mean, going forward for the next examples, I mean, we will be using learning rates,
Okay, got it.
right?
Yeah.
Okay. So what we have done now is that we try to predict between two discrete datas, right? That is two different kind of data. But before going forward, we need to understand that why actually these this why did we use this cross entropy? What is this cross entropy? You know, what is this cross entropy? We need to understand this, right? Now, what I was telling you that these are plain numbers. These are nothing like this is nothing like, you know, anything that this is any probability or anything. Later on, we might have to convert it into a probability, and then we'll go forward with that. Like I said, there will be small function. I just have written a placeholder here. In future functions, we'll be converting this into probability. Now, going for, to the next step again, what are the changes that we did? We just made changes of two things. Change was we told to my model that I need two outputs this time, right? And then I also told to my model that okay, uh, I mean, while training, basically I used is cross entropy loss. We switched from MSE loss to cross. Yeah, yes,
Anand, sir, one doubt.
yeah.
So the weight correction formula, will it be same here, like current weight minus learning rate into weight dot grad? So is that the
As
same here?
yes, yes. The formula is same, just the loss has changed.
Okay. But where it is shown here, like that formula?
No, okay, okay. So in last session, now we, if you recall the last session,
Yeah.
that is what we did is we removed the manual functions, right?
Yeah, we did with optimizer, right?
Right, exactly. So we used a step-by-step function. That is what it is doing. It is
Okay.
calculating all output. It is calculating loss, and all of those functions are automatically taken
They
care
op
by
okay.
optimizer, and
Okay.
then we are basically we are stepping with the optimizer step and everything, right?
Okay.
This should be
Good.
the
So that
last.
is inside this optimizer.
Yes, I mean, so it is happening. I mean, the process is same. We are calculating the loss, and then we are basically updating the loss, right? And then we are making our optimizer to 0 again, so that no accumulation takes place. Now calculation is same, and hence the functions are also same. These functions will remain same for a while as of now, right?
Yeah, good.
Okay, okay, all right. Now next we can go with, we need to understand that why we have taken this categorical loss. So how does it works now? We'll have to understand that why categorical loss is required, right? Now it is not very much different from mean squared error, but yes, I mean, this will be kind of new learning maybe for a few of you people, and it will also unfold few of the new things here. In mean squared error, it was simple, you know, that there's an input and there is an output, and what you do is output minus input, and then you square it off. Why did you use to square it? The reason of squaring was because we want to penalize more. We want to penalize more when error is more, right? So more the error, more the penalty, right? But this time what is happening, some of the things have changed. Now let's say if uh, this is my category 1, here is my category 2. Now here, as of now, you know, this is very simple. Even if you say that even if I draw the line here, I will be able to tell that, yes, of course, even that will work. But obviously real time data is somewhat more complex. The real time data becomes more complex, so we are just learning a concept as of now. So this is what I want, that okay, I will first start, my model starts learning. Now we will see how does this model visualizes. Model starts learning, and now This red dot is, let's say, making the guess. So it says that I give my model an input, and it says that it is present here. It should be present in category B. So the penalty, the error is huge. This is the error here, right? This is the error. The error is huge. So next, I just need to come up with a small formula, because this time I am dealing in probabilities, right? So how it is going to say that probability of X being category A is, let's say, it will say, so ideally the output, how is my output going to look like? What I was saying, that it will say that output of my category A will look 0.7, and category B will look 0.3. So this is 70% and this is 30%, right? So this is how it will give me an output. Then my loss needs to say that, okay, is this error correct or not, right? So this is what I need to calculate probability with respect to my original input, and hence my loss function is changing this time, right? So what do I need to do? I'll, I need to calculate prob how much how much my probability how much my probability is away from real one, right? Now you could say that from real one, you could say that, what you could do is, let's say, if the real probability is 0 point, let's say, in ideal case it would be 1 or 0, right? 100% probability, because we know it, obviously. Now if it is saying 0.3 and 0.7, the error is more. You could say that, what you could do is, you could simply 1 minus 0.3, and you could do this. We are doing something like this only. We'll be doing something like this, obviously, with small uh, variations, just with a small variation. So basically, the loss function becomes, what is the loss function? But they also want to penalize, right? They want to penalize it. That is, if the error, let's say now the error between 1 and 0. So let's say this is 0, this is 1. They want to penalize that if my error is less, let's say I will penalize less. But if my error is, sorry, if my error is more, I will penalize more. But if my error is less, I will penalize less, right? So they want to do that. So basically what they have done is, obviously, first thing being, I'll just discuss the formula in very brief. I mean, not the mathematical formula, and then we'll try to visualize that why this was being done, right? Why this is being done. So basically, my loss is equal to, let's say, my 0.1. I have two categories, 0.1 and or I have three categories, 0.1, 0.7, and it will become 0.2, like, right? 10%, 70%, and 20%. You don't need to remember all of these things, but this is for general understanding. At least you should know functionally that why did we use categorical cross entropy. But yes, for people who might like to appear for technical interviews, this is very much required, right? You will need to remember this, and at some places, because this becomes the base of many other advanced functions. Now the loss is, they say that loss is equal to, we calculate the complete loss, that my true values were, what was my true value? 0, 1, and 0. True values, that is probability. Let's say probability of category A, category B, and category C, right? Now they say that, what, you do one thing, 0 into whatever the 0 into 0.1 plus 1 into 0.7 plus 0 into 0.2. So they're trying to sum it up, basically, right? And they have introduced one small function here, that is logarithm. Why logarithm? What does logarithm do, right? Please do not be afraid of this thing. uh, Logarithm is nothing, but logarithm is just a way to penalize it. I'll just show you a small function that I right? Here is my log explorer. What does my log do? Log between 0 to 1, right? Sorry, this is exponential and this is log. So exponential and log. So first we calculate that what is, let's say if my x is 0.01, its log will be minus 0.46, and log x, the loss value, it will be 4.6. You know, the huge value when this value is less, when it is closer to 0. You see, the penalization is more. As I go 0.99, I mean the probability, or it is more confident. So when it is more confident, it says I'm 96% confident, then we penalize it less. If it is less confident, we penalize it more. So this is the whole function of log. There, I mean, not making it very complex. There is no magic that log is doing, right? And log is actually, just opposite of exponent. If this is your exponent, you see the graph functions, they are just opposite. What is exponent? E raised to the power, right? So if x is equal to 4, and I'll go with, so exponent is this, right? And its inverse is basically log. So as of now, what is log doing? So if you inverse this function, it becomes log basically, right? What it is doing, why did we use log as of now, or in machine learning most of the times? Log is mostly used for two things only. Whenever you see log, it is log at one place is used for scaling up or scaling down. That is one function, but now people have stopped using it for that function. Most of the function, it is here in this case because it is all about penalties. So basically we want, if it is less confident, we want it to penalize more, but if it is more confident, we want to penalize it less. uh, right, more confident, we want to penalize it less, right? So this is why log is used. There is also significance of minus log. Why? Now here, if you see, this is my real value, this is my real value, if this is my real value basically. So ideally, the log of 0 to 1, log of 0 to 1 is usually is always a negative value. Log of 0 to 1 will be a negative value always, right? And hence we just want magnitude, so I will just attach a minus here. So now my loss functions become positive and I receive a loss function. This is my categorical loss. There are more advanced loss functions also that are available. You can use them. For an instance, it was automatically suggesting the BCE loss because it is a binary function. It was suggesting BCE loss, right? But yeah, we'll discover them as we go forward. Now, this loss function, you can use it for most of the things. You can use for most of the things. But the important point to remember, I mean, for functional, the important point to remember is that you may not remember this function altogether, right? There's no need also. You just need to remember that mean squared error is for continuous values. It is for continuous value. And cross entropy function loss, cross entropy, right? Entropy itself means basically we are trying to calculate the difference here. The cross entropy is basically, it is the difference between, so this is for categorical loss. This is for categories. Whenever we are trying to find categories, this is the loss. Now, if you see also one point that I want you to remember, that these are very simple and plain functions. There is no fancy thing in logarithm, right? Uh, was there anything very too fancy in logarithm? Did you find it very fancy thing or very complex thing? Team, did you find it very complex?
No.
Right? Even if you might have heard it 100 number of times, but believe me, there is no complexity in it. There is no complexity in all of these things. Why? The moment if I would just have been writing before you that, what, now if I want to make this as a function, and if I want to make it scary, right? I can write my same function as summation of, let's say I can write the same function as summation of I to I is equal to 1 and summation minus log of, you know, uh, I guess it will be 1. The original value is like it was 1 0 1 0 0 comma, so it will be original value of, right, starting into something, sorry, it will be 1 minus log original value ix minus something, uh, the loss value, right? So this becomes a scary function, and if I just introduce you this, I mean, it becomes boring. There is no point in even studying it. But as we open up this function, we visualize this function. So these expressions are just a way of shortening it. These were basically when you are doing, these expressions are good when you are doing your own research for mathematical research. Now I have been working on this, so it is like a notation. It is just a notation that, okay, this is what notation we have written, and it is good for us. However, when we are studying any new subject or especially AI, then obviously these functions also need to be broken down. Anyways, right? So here we are. This is my log function, as simple as that. And usually when I am using this transition, I need to attach this minus log. This value minus log is, it this is the original log function. If you see, this is the original, blue is the original log function. When I attach minus, it becomes this, the mirror image. That's it, right? This is y is equal to log x, the blue one, right? And you see, the value of original value of 0 to 1 is always negative. It is always negative. So I just want to make it positive. That's it. And this is just an exponential function. I just want to tell you that log is actually inverse of exponent. That's it. As of now, we do not need this exponent, and hence we calculated this whole error here. This was the error that we were calculating. Got it. Right. Now I have one more demo here that I would like to represent you. Just give me a second. I'll have to find it out. Okay. So now this is a function that I had. Basically, I wanted to show my thing that at least for till the time we can visualize things, because when the data is too huge, till the time we can visualize, we'll try to visualize few things. Now I want to visualize this being separated by a line. I'll have to get the mesh here, I guess. Mesh points tensor to device is not required. X underscore np, x underscore np, and the other one is y underscore np. No worries. X underscore np is equal to, so this is just for visualization purpose, team. If you see, this is what my model has learned actually. This is what my model, now ideally this is not perfect thing, but this is just for visualization, right? Because obviously when we are predicting the categories, so it tried to go through the whole learning and try to predict this. So we are trying to predict that, okay, beyond this line it has predicted this category class 0, and beyond this line it has predicted this class 1. These are some of the false positive that it is still having, right? So this is what it is. This is what my model has learned till now, right? And here also, if you see in the corner cases, here also it has spilled up something, right? It did spill up something. For categorical cross entropy, there is one more thing that we would like to just reiterate over thing. And then we would go to add one more function, that is one more data point for multi-class classification. Okay, just wait a while. I'll have to restart this thing. I mean, so as we go forward with more and more complex data types, the visualization is becoming more and more tough. So I have to use more and more libraries in order to make it visualized well. Okay, so here we are, and I'll run it here. Right. This is again 2 moons data, right? The idea is just basically so that everyone is seeing that how this whole thing is getting again uh, trained, So we just want to visualize that. So I'll just go for initialize, reset the model. Okay. So this is my initial learning, all no learning has been made when as soon as I initialize, and as I go, my loss has started decreasing with each and every epoch. You see, epoch 3, my loss is decreasing, my loss is decreasing, and this is my model is learning. Okay. And now it identified, initially it was, uh, you know, trying to differentiate between 2 to 3 points, but now it has identified that, okay, these are just two things. And then it has started to learn this. I can just go ahead and run 5 epochs. I can go ahead and run another 5 epochs and another 5 epochs. And so as we see, every time it is happening, this is real time training. I mean, I'm running it on Gradio. Basically, it utilizes my server, and I can, from that server, I can temporarily run a small server on my local system, and I can show it to you, right? So this is live training. This is real model. I mean, no dummy model, no dummy data, right? So this is happening as and when, as we go ahead. I can go ahead with 10 epochs. I'll just run an epochs. Okay, I'll let it run. Right. And now if you see, it has better started classifying, as some of the false positives are there, but it has better started classifying some of the data. So this is what is happening. Now, there is one more thing we would like to revisit again. That is again the categorical cross entropy. Although I explained you in a very simplest format, but I just want to show to you once again the same training we will be revisiting, where we would be seeing how does categorical cross entropy get calculated each and every time. We just want to see that calculation once again, so that we do not have any of these things, any doubt for us. So let me just uh, rerun that. Okay, I guess this is for Cross-Entropy. Okay, okay. Just hold on a second. Okay, so I'll just run it live. Okay, now this is basically nothing that what we had actually done, uh, the whole thing, what I was talking, this is the same calculation. Although I then decided that I would basically go from, we would learn basically on the whiteboard itself. Now, basically, this is like, let's say, initial raw scores. These initial raw scores, they get converted into probabilities. We are converting them into probabilities. And once they are converted into here, they are converted into probabilities 62%, 23%, and 14%. And this is the final probability. And then after finding the final probability, we find their logs and we sum them up, right? And this is how, forget about this function as of now. This is the same softmax function basically that converts any list into probabilities. It converts any list into probabilities. So this is what it does. So basically this is what class 1, class 2, and class 3, the distribution will look like. Now the same, extending to the same playground, basically, how does this calculation actually happens? Right. Now here, instead of 2, this time I have taken 3. I have taken a different data set. If you see, these are, this is green, this is brown or red, and this is yellow, right? Now, this time I'm taking the same theory basically, and you see it has started first. It has directly gone and actually very simply done in the first epoch itself, because obviously this data is very simple. But if I just go ahead, it will try to remove any false positive also that is present. Now, what is happening here? This is the real output that my model is splitting out. This time it is going to split out what? 3, right? Each and every time it is going to split out three things. So it is 1.67, 0.26, 0.15. So it gets converted. Softmax is used for converting into probabilities. If you see this, if you add up all of this, it is going to add up to 1, because now it is a probability. Initially, my model did not return any probability, but then I use softmax function. Softmax was also one of the functions, activation function. So we use softmax also in activation, right? But it was outer activation. It was not inside activation. Inside activation was ReLU and Tanh only. And hence why softmax is used outside, because whenever you have any such kind of problem where you need to convert your output into probability, you use that, and hence you use it in the end. You use it in the end, you do not use it in between. So softmax is here 0.71, 0.17, and then the probability class of this is done, and you basically minus log of p true. So this is p true, right? And using the same formula, basically we are able to calculate this loss here. So as we go forward, basically this training loss is decreasing, and similarly this 3 data set we are able to do with this 3 data set. These are, we are able to divide them into 3 different categories. But this time, what might have changed with my model? The only thing that will change with my model is how many number of outputs do I need. And if you see, the number of outputs has changed to 3, right? Because this time I need probability of these 3 classes. And this time, since I earlier I just had two, so I could have used max. I could have used max even this also. But yes, I mean the standard procedure is we first convert them into probabilities. I could have used max in this, right? That whatever is the maximum, give me that class that it belongs to, that minus 1.67 would be the maximum. Even in this case, I would say that 2.33 is the maximum. I could use that also. I mean, no harm in doing that if you want to eradicate. But yes, going forward, lot of functions will be needed. So you can use this function, basically softmax. It will automatically convert your list into set of probabilities, and these probabilities will add up to one. That's it, right? And now let's try to basically run this program. That is, we will try to create our own program for the same thing, that is three categories problem. I will very quickly run over it. The reason being, this is simple. I'm again using the same problem, three category problem, right? I'm again using three problem because we just have to switch to a more explanatory problem, that is a more real world problem, or we have to take another step towards the real world problem, not a real world problem, but we do have to take a step, because this is, once we have learned to differentiate between these categories, then basically we can go ahead with various images, various kinds of images you want to differentiate, various kinds of data, text data, image data, even audio data. All of this data could be used by a same categories. But yes, instead of linear layer, there are more complex layers that are just suited for every kind of data. This will be the difference that we will see till the end. And just with the generative data, there will be actually two models, two parallel AI models that will compete with each other to generate and test the data. That So these are the architectures that we'll see forward, right? Let me go towards, I mean, first, the dataset name, I guess it was three blobs data. Okay, make blobs, I guess. So we'll just use a sklearn for generating that. Load three blobs data and visualize it. Okay. Oops. It has actually generated everything for me. Basically, it is working on my history, and what it is trying to do, that if there are any, it actually copies my style of writing the models also. Because I mean, it is generating everything that how we are trying to visualize. But I mean, will not go in this way. I mean, everything perfect. It has done everything right. Yeah. But let's try to basically write our model ourselves. So obviously we will quickly do it. Don't worry. We'll just take 5 minutes for doing it. Let make blobs, and we'll just load this blobs here. This we will do. Next is, the reason being, I don't want to confuse you with lot of theory, that so when you, if even if you go with chat gpt, you try to generate, it will generate some simple things, but sometimes it generates lot of extra data. Now you need to know that if this data I need to consider or I do not need to consider. So this is something that we'll have to learn. Okay, we have done this. Next is, basically we'll have to create our model. So okay, since I did take 100 things, so it has all automatically taken my model with same sequential 100 models. Okay, done. Next is, what I need to convert my data to tensors. This is my tensors. I need to convert my data to my tensors. So this is the same thing that we have been using, right? Okay, got it. My data has been converted to tensor. These are my errors, and it has actually copied my epochs also, basically. Okay, and here we have, right? and then epochs. Okay, I will loss history. Will take this. For now, I do not need these many epochs. I'll just go with 120, and that's it, I guess. I'm able to train my model with this, right? The same thing, the same code that we had written earlier, the same. Okay, 100 out of 120. Okay. So this is nothing basically. Actually, it is printing in every 100 steps. This is trying to print in every 100 steps that what is my loss. So it has printed with 1200 epochs. And once I go to generating my model, so this is my model, and I can go ahead and generating, let's say, tensor underscore x of uh, 0 to 3. Sorry, my name was, I guess, x underscore tensor or something, x underscore blobs underscore tensor, x underscore blobs underscore tensor. This is my output. If you see, it is giving me output in terms of 1. Oh, hold on, 0 to 3. The output should be 3, right? This should be my output. It has taken 3. It should take 3 inputs here, because x underscore blobs and sample centers 3. Okay, x underscore blobs. So these are the small mistakes that AI can make. X underscore blobs of 0. Oh, it is okay. It is taking x and y only as of now. In that case, it will be just 2. Mm, 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 mm. Okay, 0 of 3. It is giving 2 probabilities only, and basically it is giving me a point. I will need the probability to be x of 3, and as I get x of blobs dot tensor of 0 to 3, 0 to 3. Okay. Oh, sorry. Yeah, prediction predict is equal to this. And if I go for predict of 0, 2 outputs, it should be 3 outputs ideally. 3 classes are here. Evaluation blobs dot tensor torch dot max. So this is basically it is again using torch dot max here itself, but okay. But this is, it has given just the maximum values. What is the maximum value? And it did not actually pick up the class. So it is not picking up the class. Y of 0, y of 0 to 10. I guess there are just 2 values here. There are not 3 values, and hence and then it has not taken three values. Random state, make blobs, blobs three classes, feature 1, feature 2, feature 1, feature 2, x underscore blobs is okay. I'll have to look for it, this function basically, because it is taking two features. I mean, it is not taking three features as of now, but two features is obviously x and y. So it is taking x and y, and based on that, the labels is present that okay, if the data is present in this area, if it is. So yeah, I mean, basically we do not have in that case three classes to predict. We're not getting three classes to predict. We should be getting three classes to predict. Yeah, it is 0 and 1 only. I hope it is not mixing up with previous data. Two data only, and then okay, this is 0 1 2 0 1 2. Here we are having three categories if you see, and I guess even here also feature 1, feature 2, 3. Okay, three categories are here. Fine, got it. And in that case, y underscore blobs, why is it not printing 0 10? Okay, y underscore blobs is also having two categories. Okay, sorry for the confusion. Actually, I was looking at x and y of previous data. So we were actually using x and y of previous data. Okay, even here, predict underscore blobs, torch max, x underscore blobs underscore tensor, y underscore blobs underscore tensor, predicted blobs. It is not giving me class, although here is 0 and 1 class only. It is not giving me two classes. 2317. Anyways, no worries. We'll have to use the softmax here. I mean, without using the softmax, that won't be possible, I guess. Or based on that, we will have to assign it to a class. I mean, what it is doing as of now, it is automatically taking the label. Now, based on that, we will have to check that whatever is having the highest probability. That is, let's say if it is predicted blobs, this is the predict function. Now, ideally, we will have to go it like this: predict of 0. Now, whichsoever is having the highest probability, that will be my class, but it is giving me just 2 as of now out of 3. Let me go back and fix it. I'll not take too much amount of time because we have one more example to cover, which is much comprehensive and a bigger one. I'll see that somewhere this variable might be getting mixed up due to some reason. Never mind. This also data I did take up for the example. I was not very much knowing this data set. I wanted to show basically learning that happens in three categories. And although it is showing me that it has learned in three categories, but yeah, I'm unable to find out those three categories where they are and where they should be. It also might be possible that it might have just tried to learn something else. And in visualization, we might have made some error here. Obviously, this visualization is made by Trivedi, so there might be a chance that it might be making some error here. Yeah, anyways, I'll move on to the next example. I'll fix this one, don't worry. And when I give you in the workbook, basically, ideally, I'll fix this example. But yeah, we have a bigger example to study basically, and it is of basically, I want to classify images, the images that I have already taken, classify the MNIST images. MNIST, what is an MNIST image? Basically, MNIST is the OCR images. You know, this time we did create a model where we tried to classify those images using AutoML, but this time we will try to classify these images using ourselves. That is using our own model. We do not want to classify those images using AutoML anymore. And this time I also have around 9 to 10 categories wherein I want to classify this data, right? And 9 to 10 categories will be present. And amongst those 10 categories, I will check that which category is giving me the maximum probability. And based on that, I will decide that, okay, if class number 2 is giving me maximum probability, then this is what my prediction will look like, right? So I'll just quickly go ahead and I will start with everything without wasting much of the time, because that is comparatively big example. There are a lot of things to cover because this is a complex example. I mean, till now we have not even went close to any real life thing. So I'll just start. I'll get my data from sklearn only, from sklearn dot datasets, although we have yet not started to import the data from Excel and everything. But yeah, these concepts are important before we jump to that OpenML. And this is x comma y is equal to fetch underscore OpenML. Okay, this is fine. Return x and y is equal to 2, true. And yeah,
Yeah, Anand, can you just brief about that classify? What does mean by that? Whatever the first exercise we did, right?
yes,
From the
yes,
lift classification and detections.
right.
So is it the same under the this
Yes,
exercise?
we are still doing classification only.
Okay,
We are still doing classification. We are still following the same method, but just the data set is more complex this time,
I see. Okay,
right? Nothing will be changed, right? Nothing is going to change. That the data set is going to be more complex. The data, it will be huge data, right?
okay,
So this is what we'll be doing, right?
yeah.
So what we are, I'll just display this data. Just wait, hold on a while, right? And just go visualize MNIST data set. So if we go, so this is my data set. See, so what is my data set? I have around 9 labels, label 0, 1, label 1, right? 9, 4. So these are very small size of images. And since they are small, they're handy to load and run on CPU, etc. But now my job is that I want to train my model. I want to train an AI where my model should be able to classify that. I will train on this, and then if any handwritten image, if I give it to this in this format only, obviously it has to be in grayscale and anything. If I give any handwritten image here, then it should be able to detect any unknown image. But obviously for now, we will divide into test and train. That is, we will take some images on which we will not train it at all, so that we get to know that, okay, this is something unseen data, because the whole point of AI training is running on unseen data. We have to run the model where the training has been done on training data. Then we will separate a small test data on which we will only perform the testing. And this is from the testing we will conclude that how much my model has learned. Because on the data on which you have already trained, it is going to predict with 100% accuracy, right? On unseen data is the key thing, that on unseen data on which it has not been trained, it should still be able to predict any one of these things. So this is going to be small complex example and first ever example, that is we take the first step towards something real life. I mean, although in today's world there are already so many good OCR trained and everything, so they all initially at a very small level they work on this thing only, that they read character by character, and then each of the character gets converted into this kind of thing. These are handwritten images. So let's start by, basically we will start basically by converting this data into tensors first, what we have already been doing, right? And then once we convert them into tensor, then we will use the same model, same categorical cross entropy loss, and same optimizers to train everything. And then we'll try to visualize that what we have actually learned, right? So let's start. So I'm not doing anything new. My whole aim is to tell you that whatever the basics we have learned, anything can be done using it. Now, can you do dog versus cat classifier? Yes, you can. Or can you train anything that identifies various different objects in the real world? Yes, it can. It can do that, right? But the whole point being, we will have to make our models more advanced. But again, even with this models, there is no limit what you can do. You can go ahead, you can try what it does, what it does not. uh, if time allows, basically maybe tomorrow I will prepare one small program that is of classification of, I guess it has 20 different real world objects. But yes, I mean, these models are very small as of now, very simplistic model. For more complex we need CNN models, right? Anyways, talking further, like I have already loaded my data in X and Y, right? So first I need to convert into tensors, right? I'll go ahead and convert it to tensor, the golden step that we have been doing all of the time, right? So let's go ahead and convert it into tensor. Okay, x underscore tensor is equal to torch dot tensor, and I will have all images x, I guess x and y, right? X. I'll this time I'll manage the data type torch dot float 32 and then 64 y tensor x tensor y tensor, right? Okay, here I do have a problem, I guess. Too many dimensions. Why is it going torch dot? No. Is it my data is present in? Okay, I guess my data is present in string format. No, it is in pandas format, I guess. Why of 0 5? Yes, it's in string actually, I guess. So just Okay, fine. I have this. I guess the difference was with as type function. I was doing a mistake here. Right. Anyways, these are some small nuances of AI. Right. Anyways, now this time, what is the length of my data? You see, these are this time there are a lot of many new things that we will discussing. The procedure is going to be same, but there are new things that we will be discussing, right? What is the total length? Till now, we have been working on 50, 100 data types only, right? This time, x underscore tensor, x underscore tensor underscore MNIST. What is my data type? Oh my goodness, 70,000 images, right? I am going to train on 70,000 images. So that is going to be huge. So what do I do? Should I load everything at once into the memory? No AI in this world will be able to do that. And this is where batching, the process of batching comes into process. What do you do? And this is not something new that I have to teach you. You do it in everyday life. Whenever there is something that is too huge, you basically divide it into batches. Nothing new. Divide it into batches. So what you do? Depending on the basically size of your RAM in your system, and sometimes then when we'll switch to GPU, depending on the size of GPU, etc., right? You will be loading how many images you want to load in one batch. As of now, I want around 64 images to be loaded in one batch. Ideally, we keep it in sync with the bit size, either keep it 8 or let's 16, 32, 64, 128, right? uh, then either 512, something like that. So try to keep this number, right? So as of now, I'll take a 64. Now what does it means? That at one time my model will consume 64 images for training. Earlier we were loading the whole data at once, but not anymore, right? We need the batch size this time. I need to go with the batch size, right? So as I go with the batch size, okay, I'll take a batch size, let's say of batch underscore size is equal to 64, right? And then, okay, now it's time to basically make my model, right? But for making my model, I guess, okay, hold on. Create a model. I do not want to use the PyTorch function basically because I have not yet discussed about it, because I do not want to use DataLoader unnecessarily. There's no point in using DataLoader as of now. Okay, hold on. Okay, all right. Let me try, and then create a model. Create a simple sequential linear model with ReLU. Okay, the simple sequential model. Now, what it is doing is 28 by 28 pixels. It is automatically using. That is, this we'll have to manage first, because there is basically 28 by 28. This is the size of the pixel that one model is going to input, and this is the hidden layer. Now, if you remember, just hold on 1 second. I do have that linear activation function thing. Since we are dealing with the images, now let's say this is my uh, right. Right, this is my, and I'll just take some random image here. I'll just take some random image. Let's say I'll have to look.
So Anand,
Yeah.
just for my curiosity, this CPU, this 70,000, right? The processing of the image, is it required the GPU or CPU? It's fine.
uh, CPU will actually speed up your multiplications, the model training.
Hmm.
For storing usually the images, I mean, this is basically you need to load the images at once, right? It is just like any software that we are dealing with,
Right.
right? So for that, basically GPU is not very much required. As of now, we have not even touched GPU. We are doing everything on CPU, right?
Okay.
Right. Now, if you see here it is, I have displayed this image in 16 by 16 cell. I'm displaying this image in 16 by 16 cell. So my original image, I mean, wherein I'm talking, it is in 28 by 22. Sorry, 28 by 28. What if I flatten the data? You see, this is what my image looks like. But when I flatten the data, it will become in one dimension. So let's say if this is 16 by 16, so it automatically becomes, let's say if I calculate it and if I go with online calculator, rightly. So if it is 28 by 28, 28 into 28, so it becomes 784. And this is how that number comes into picture, right? So basically what I'm trying to tell my model that, you need to load 120 because my MNIST data, if I go ahead and talk about my MNIST data, this is, it is telling that what is the shape. Let's try to understand the shape of the data. So x underscore tensor underscore MNIST, right? This is the data. I'll go with shape function that tells, it is telling me that complete data set. But if I go with 0th column, just the first image, right? Shape is 784. It has already flattened it basically. But if I pick up my original image, this is my original image of 0 dot shape. Oh, this is also 784, I guess. It has to, if I want to visualize this image, hold on, let me visualize this image. Visualize index 0 or visualize image n of data MNIST. Okay, so image number 5 and image number 0, it is trying to visualize. So if you see, this is my image. Now what it has done, actually, in order to visualize, it had to reshape my data. It had to reshape it to 28 by 28 because, initially my data is present in one long uh, array. If I just try to print this data, if I just try to print this data, let's say I'll try to print this data, MNIST of 0. So it is one long thing. But what they have done, so data is basically 0 and 1 only, right? So here they have put all of this data here and they have returned us in form of one long array. But if we want to visualize it for training, this is ideal. I mean, this shape is ideal. That is 784 is ideal. This is 784 pixel, right? And these are the pixels that I was talking about. These are the pixels that I was talking. So these are the pixels that I'm talking about, right? Now, these are the pixels, but if I want to visualize, I will have to convert it back into 28 by 28. I'll have to convert it. So then only it will be able to convert those images into, right? It is converting those images into numbers, right? If can, let me try to just print these pixels without flattening, right? I'll just say that show me each pixel color without without converting into 20. I do not know it will be able to do it or not. 28 by 28 in flattened format. It is not showing me colors, it is just printing it out, because obviously it will have to use some library to display, although it has given value of each and every pixel. If you see, it has given value of each and every pixel, 0th and fifth column, all of the 784 pixels, right? So this is the data this time we are pushing. This is the data. Now this is why 784 is there. My output last is 10 classes, 0 to 9, 10 classes, what I was talking about. I do not know, there might be something wrong, or I might not have understood the data right, because I also tried, I wanted to show you three classification thing. So I picked up that data from sklearn, I guess. Maybe there might be some other dimension involved in it, but I'll update you once I see that. So I thought, let me pick it up. Now here it has 10 data. So the thing goes very simple, that based on my input can be anything. My input can be anything. It can be your picture also, right? If you want to differentiate, or you want to differentiate between various family members of yours, this also can be done. This is how basically the camera things that identifies the person is done. I mean, this is the first step. Obviously it has a more advanced algorithm, right? This is not a simple model, but this since these models are so small, they can fit into a camera hardware also, and they can be very fast at looking at a person and identifying that, okay, here the person, this is the person uh, that is wanted, or this is the person that is uh, that public I mean, maybe the authorities are hunting or something like that. So this is how these kind of systems work. uh, this is a very simple example as of now, right? Because just for information, I am just trying to show that model, how does data works with model in very practical or very common models. Usually CNN, convolution neural, CNN is used for image processing or image functions, basically image AI. CNN is nothing. CNN is just another type of layer, just another type of layer. It has, I mean, it is nothing out of the world, the same like linear. There is CNN, there is RNN. There are just small functions. They also have neurons. They have same neurons that we are using in linear, but their arrangement is different. Only arrangement is different. And basically we will be covering more RNNs, because we have to go towards applied AI. So text and RAG, etc., are the use cases that we have to cover. We will cover CNN in shorter form. Maybe one lecture or so we'll cover CNN, right? So okay, here we have my model is being prepared now, done. Okay, my batch size. There are other smaller things also that I will have to, I guess, mention here. Okay, once my model is done, next is I will have to go with the cross entropy functions, right? So criterion MNIST is equal to NN dot cross entropy and optimizer. And I've mentioned a small learning rate here, and I can change this learning rate when I want, right? Model dot parameters MNIST MNI model underscore MNIST. I guess this is the right one. Right. Okay. Okay. I'll go ahead. And next, after this, I will start with the training part. Epochs is equal to 10. I'll go with at least 10 epochs, right? And for epoch in epochs, I guess now I'm writing this again and again so that it comes to your mind, every time it comes to your mind that, okay, why we are using this. There's a small difference this time, you know, okay, it is telling me with, hold on. I guess it will have to come with data loader. Generate training for MNIST. Data loader, it is using data loader itself. I do not want to use this data loader as of now. Just hold on a second. Because I unnecessarily it will make it more complex. So I just want to avoid that complexity. Okay, print and flatten it out. I guess in the last, either if we have no other option, that we might have to use the data loader. Okay, let me initialize the data loader, because the reason being MNIST underscore, or else I'll have to write the whole loading function myself. Now this data loader, what it is doing basically, this data loader is, it will manage those batch, I'm not training one by one image. So I want to train uh, all of the images, 64 images at once. So this will basically speed up my training. Or else, for starting, what we can do is, okay, generate training without data loader with one image at a time. It is actually making it more complex. There's no point in doing this. Okay, model set image training, and image is equal to unsqueeze. Forget it. We'll use data loader. It is one line, and I'll explain it to you. MNIST underscore data loader is equal to data loader and x underscore tensor. What are the other variables? MNIST data loader, and it should include my batch size, comma, batch underscore size is equal to 64, and shuffle is equal to true, right? I'll have to import the data loader. So data loader is present in a package called from torch.utils import. Okay, from torch.utils data loader, and here I got my data loader. So this data loader, basically what it is doing, I do not want to complicate things unnecessarily, so I'm using as many less functions I can. But I guess since we are now loading all of the images at once, so we'll have to use this data loader, or else we'll have to do a lot of image manipulation, picking up one image at a time and then sending it. We might end up wasting a lot amount of time. So basically this will load the data, right? And now our basically training sample training code becomes very easy, right? So I'll go ahead for epochs, epoch in range of 5. This is my number of epochs, right? And for I comma data in enumerate, my data loader name should be here, MNIST underscore data loader inputs, and this is my inputs and label. It is printing all of them. Okay, and here I do not need this. So basically now I am able to use the data loader, and my function will be very simple now. Optimizer dot zero grad outputs is equal to model underscore MNIST. I guess this is the one. Let me have a look so that we don't end up wasting our time. Optimizer dot and loss is outputs. Inputs, okay, inputs, this input is going here and this label is going here, right? And then loss dot backward optimizer dot step, and that's it, I guess. Let's print what it is doing, right? Let me print now the loss and print loss dot item. Okay, I guess now there's a problem here. Too many values unpacked, and okay, too many values unpacked. So there's a dimensional mismatch here. MNIST data loader 64 inputs comma label running loss epoch 5 range MNIST. Okay, data loader MNIST data loader. All image pixels and batch size MNIST dataset. Yes. Okay, hold on. I guess the problem becomes here. X underscore tensor MNIST underscore data loader. Okay, this is the problem. So it is not getting along with this. Maybe pixels underscore tensor. Create training loop with 64 batch size. And data loader. Okay, I guess there was one more function that had to have, because the reason being, ideally we should be loading the data from PyTorch only, but here I'm loading the data from scikit-learn, so sometimes the data mismatch happens. Why tensor MNIST and then batch train MNIST inputs. Okay, it runs. So yeah, there was a mismatch basically because we were taking from scikit-learn. Right, my data is getting trained now and the loss is gradually decreasing. I have used for it has automatically generated for 20 epochs. After 20 epochs, basically there are few more best practices of model training that we have yet not followed. That is, we did not divide our data into test and train basically. So we will have to divide that data into test and train, because then only it makes sense. As of now, we are training whole of the data and we'll be testing from the training data only, which is a wrong practice. But that's okay for learning for now, because as we move forward, we'll start doing that. Right, my model has trained properly, and let's try to now check that what my model is basically predicting. I'll just go to model.eval and I'll start printing it. Model of I'll just try to load one batch here. MNIST underscore my data name is x underscore tensor underscore MNIST. So 0 to 10, I'm trying to print the first 10 images. It returned into an error. Again, the problem is same. I guess it is taking a different dimension altogether. This is creating unnecessary complexity here. Hold on now. I'll have to basically go with x underscore tensor unsqueeze of 0 0 sample underscore image this. Okay, now we'll try to predict one image. Output is equal to torch model sample and then max output. This time I'll use Softmax. I'll not go with this. Right. Okay. First, let me print the output, and again, it is still not able to do it. Oops. Start. Grad. Multiplied 1 into 74. Mat1, mat2 shapes cannot be multiplied. Create a prediction function. Unsqueeze. Okay, we did this. Image.tensor model input image. I guess it is same. Let me try this function. Yes, it works actually. Why is this not working in that case? I'm sorry, my bad. I'm using the wrong variable. But yes, still the problem is same. Model underscore MNIST. There's no model. The model name is model underscore MNIST. Right. And yes, we're done. Output. Okay. So how many output do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. I have 10 outputs. What do I want to do? I want to convert them into probabilities. Right. So there is a simple function torch dot softmax. I can pick up the longest one, but let me do it. I mean, the best way is output, comma, dimension is equal to 1. And this is my probabilities. Because why probabilities? Any UI, anything, this is human readable. That this, if you give this to anyone, to your customer or anyone, I mean, he's going to get freaked out. But if your model, you say that it is 98% confidence level, the customer also understands, humans also understands, and everyone understands that, okay, model is having confident level of 98% or 99%, right? So this is how it gets to. Now, if you see my model, one of them, I will just go with now torch.max, torch.max with the probability. Oh, it should be with the probability underscore class. Probability comma 1. This is the probability. This is the one that is having highest probability. That is 96% probability. The image number is 5. What was the original label? You know, I did take for y x underscore tensor MNIST 0. Let me find out what was my original label actually. So I'll go ahead and underscore y underscore tensor underscore MNIST of 0th column. I see it is 5. This is 5, right? Let me now try with something else. Basically, I'll take some index. Index is equal to, I'll write here index so that everything gets automatically printed out. Output, and after output, basically probability. This is my this is my probability, and this is what is present. Print predicted is this, and we have also the actual one, right? This is the actual one, right? We got this. Why is it showing this? Predicted, comma. Okay. All right. So number 10, let's see, 3, 3. Okay, cool. Number 11, 5 again, 100. The other point being that we did train on all of our data, so obviously this is going to be very much accurate, right? So now, if we have absorbed this, although there is a lot to talk even on this, right? Because now once we have touched one small milestone or first milestone, there are certain things that or certain theory that we need to understand, and even certain things that we need to understand. That first point, what we need to understand here is that the first point being that we should never train on all of the data, right? Never train on all of the data, on all data. We'll have to understand few very important terminologies. Never train on all of the data. Always split the data. Always split the data, right? You can keep your split. The more better your test data is, the better your model will be. So better, because now we'll start using that test data. Better your test data, better your test data, better will be your model. Better your model. Then fourth, what is significance of accuracy? How to evaluate a model? How to evaluate a model? What are the steps to evaluate a model? That is, what is there are for evaluation, how do we calculate accuracy? Although the accuracy is right guesses versus the total guesses, right? Obviously, but yes, we need to understand what is F1 score. Nothing, this is also not something very fancy, right? And then we need to understand what is confusion matrix. We need to understand what is confusion matrix. How do we need to evaluate all of these things, right? How to evaluate a model is very important. And then basically, obviously, although I will take one more example here before we go. How, what has a neuron learned? What did a neuron learn? What has it learned? I mean, we have been wondering about, this has neuron has learned this, neuron has learned that, but what has it actually learned? It's time to see that actually, you know and we'll continue to see that as we go forward. There are lots and lots of what we call um, observations and learnings that we need to get from this code. So let me first run a small visualization wherein we will see that what a model has learned. It took me some substantial amount of time to build this, because again, as I said, that it is getting more and more complex now, but don't worry, that's my job, to break down complexity. Okay, just give me a second, I'll have to restart it. It has again gone down. Okay, done. Let me load it.
Anand, I don't know. I am seeing only that the points you just mentioned in the
Yeah.
presentation.
I hold on. I'm just I'll just set my screen on.
Okay.
Yeah, just give me 1 second. Okay. Now you can see Keyur.
Yes, Anand.
Okay, cool. So basically, this is again a so we call it basically the Gradio UI, right? This is basically data scientists or AI engineers use in order to demo some things, demo a concept to your colleagues, management, or even to a customer. Because I mean, all we have to make is algorithms. We are making algorithms, or we are demonstrating something. So these are some things that we make. And if you are into functional side, you can actually instruct your team to create demos like this. So basically, this is my data, right? This is my data. These are my labels, right? And then what I'm trying to do is I'll just load a model here. Since as of now my model is small, so I'm able to load it. Okay. So basically, what has happened, if you see, this is my first epoch, first training learning, right? What happened? How many hidden layers I have? I have 32 hidden. I have 2 layers and I have 32 neurons in it, right? What has my first layer learned? It has not learned anything, right? It has not learned anything. But what I'll do is, and you see the probabilities it is giving for my 10 classes. As of now, this is the highest one. It is giving 8, which is completely wrong. This one it has somehow able to give right one, right? Oh, sorry, it is giving 8, which is wrong again. So all right, it is giving, these are the right values, right? And it has not learned anything. Now I'll continue with the training. So okay, so what it is doing basically, it will train for another 5 epochs, and we will see, we are literally halting the training, and we are seeing that what my model has actually learned, or what my layer has. Oh, and you see, it has started to learn some curves, right? Some of the edges, it has started to learn the edges. I mean, and prediction, true and prediction is also getting correct. Just in 5 epochs, it got it. True is 9, prediction is 9. True is 0, prediction 8, 8, 2, 2. Okay, it has got it wrong. Right, actually. Uh, Accuracy shot up after first epoch, I guess, second epoch, and accuracy is already at what, 96%, right? And I can continue for 5 more epochs. Let's try for 5 more, because since it is still 4% error is still there. Accuracy has gone to 97%. Okay, now accuracy is getting stagnant. My final accuracy is at 98%. My final accuracy is at 98%, and my loss is going down drastically. It is down. Loss is very less, right? And prediction now, if you see, my model is no confused. It has just reduced every other probability to 0. This is basically, so it is giving some other probabilities very low. These probabilities are very low. So it has reduced everything else to 0. There is just one probability that is the highest. So what my model has done, and believe me, this is a very dead simple model. There is nothing in this model. But also there are certain bad practices that we are following. What we are training on the same data, we are testing on the same data. A really, really, really bad practice, right? And hence that could be reason that we are able to train with so high accuracy. Obviously, if you train on any data and you test on any data, it is going to do wonderful, right? So what we might have to do is, going further, like these are the points that we discussed, that we will split our data into 80 and 20, right? We will split our data into 80 and 20. We will use the test data, right? Then we will use some model parameters, right? We will try to understand these model parameters, and we have already looked, but we will have a deeper look at what a neuron looks like. Today we have actually covered something substantial, and it might even confuse you. So what I'm trying to do here, first and foremost, obviously I'll be giving you these worksheets, because obviously the moment immediately you run them, you will be able to recollect them. Second point, immediately by evening, I will give you summary notes. Please go through these summary notes like 10, 20 minutes or 10 minutes before sleeping or anything. Whenever you see this summary notes of 10, 15 points, what is this, what is that? I'll give you immediately, after 15 to 20 minutes, or maybe by today, in next 30 minutes or so, right? So summary notes, very important. uh, I'll try to in fact upload this video also, but obviously going through the whole video is not possible. I know 2.5 hours, again spending 2.5 hours is just not possible. So hence I'll give you those summary notes, reiterating what we learned actually today, right? Before we close this session, and I don't want to overload also, because this information was very crucial. Now, first we did learn how to use linear data, right? Linear data. Second, how to use basically activation functions. How to use activation functions. How do we use activation functions? And with activation function, what happens? Non-linear learning happens. Non-linear learning happens. This all is for continuous data. This all is for continuous data, right? Okay. This was for continuous data. Then we switched on to non-continuous data. That is, how do we use non-continuous data or non-continuous data? For continuous data, the error used was mean squared error, right? For non-continuous data, basically cross entropy is the function, is the error, sorry, loss, basically the correct name. The loss changes. Apart from that, we have not changed anything. We are still on the same training function. We are still on the same training function. We just made small tweaks, and those tweaks were that input and output of a model should be same. It should be same as the data. Then third, we used DataLoader for batching. We used DataLoader for batching. And fourth, we tried to see what is going. We tried to see what's going inside, what's inside the model. So basically, every time we train it more, so you know what is happening actually. If you this is every neuron in a layer is trying to detect some different feature. It has learned something different. You know, every neuron has learned something different. And when any problem comes, they come together and solve it as one unit. But every neuron is having a different set of learning. You see, every neuron is kind of having different set of learning. They have learned some pattern. This is for layer 1, right? Similarly, other layers will also learn something. They will also learn something. And then this is how they start predicting further. And as we go forward, this is the probability, the loss has increased, the accuracy increased, right? And final evaluation, this is basically confusion matrix and all. The basically, whenever you see something 98, 99% accuracy in less amount of time, something wrong has been done there. And what wrong we did? We trained on the same data and we tested on the same data, right? So usually whenever you, because this is very tough thing to achieve. I mean, this is not, now the moment you switch the data, you will see that, you know, testing and training accuracy will drop. Accuracy might drop up to 80% or so. 96% is just too huge, right? And some did it. What are the some of the misclassified samples? Yes, you see, it is 8, but it is saying it is 3. Here it is 9, but it's tough for a human eye also to detect if it is 9 or 7. But this one, it is quite evident. This is 4, it predicted it as 8. This is 3, it predicted it as 2, right? And this is again 3, but it definitely looks like 2, right? And this is it. So we will see basically how to make a confusion matrix and what are the things that we need to do in it, right? I guess enough for day 1 on Saturday, right, team?